I'll be talking about skeleta. I'll be talking about classical geometry of skeleta. But first, let me just go over the basic objects I'm going to talk about. So I'm going to be studying symplectic manifolds. These are even-dimensional manifolds with a closed non-degenerate 2-form. And the main things we study when we study symplectic manifolds are Lagrangian submanifolds. These are half-dimensional submanifolds on which the symplectic form vanishes. I'm actually interested in singular ones, so we ask that the symplectic form vanishes on the smooth locus. A special kind of symplectic manifold, which is very convenient and simplifies a lot of things, is called a Liouville domain. And these are symplectic manifolds which are exact, which means the symplectic form is, okay, which means the pointer is not very effective. Anyway, these are special symplectic manifolds. The symplectic form is exact, and we want this one form, this primitive, to be dual to an outward pointing vector field. And this convexity condition is the crucial thing that makes Liouville domains really nice. So if you have a Liouville domain, you can look at the skeleton of that, which is some singular subset. It's going to be a compact thing, and it's just the collection of, it's the locus that doesn't escape through the boundary under this Liouville flow. Now, because the Liouville vector field points out, this is a compact subset of our Liouville domain. In cases I'm interested in, the skeleton will be Lagrangian, but we haven't yet made assumptions that enforce that. Now, the boundary of a Liouville domain is naturally a contact manifold. And this is just by you restrict this one form, and then it satisfies a similar non-degeneracy condition. And in a contact manifold, we have an analog of Lagrangian submanifolds, or Lagrangian subvarieties called Legendrians. And again, it's essentially the same condition. It's a maximal dimensional. In this case, our contact manifold was 2n plus 1 dimensional, and our Legendrian is an n-dimensional sub-thing on which the one form vanishes. So just some examples of these objects are, you can just take any oriented surface with boundary, and take it compact. I'm just going to draw kind of a running basic example. Let's have a cylinder. And it comes with some volume form. Now, a Liouville vector field for that is a divergence 1 vector field with respect to that volume form. I'm going to draw kind of, imagine having something like this. And of course, this vector field gets much bigger near the boundary because it has divergence 1. Actually, over here, the ones on this side need to be bigger than the ones on the back side, again, because we're enforcing divergence 1 everywhere. Okay, and the skeleton of this is a curve. In this case, it's a smooth curve. In general, it's some singular curve. It's homotopy equivalent to the ambient domain. But in this case, it's half-dimensional. It's a Lagrangian. Any curve is a Lagrangian. This thing is a curve. Therefore, it's a Lagrangian. And so surfaces are the first example of Lagrangian skeleta. Now, a Legendrian is a finite union of boundary points, and really that tends to show up as the boundary of some Lagrangian. So I've drawn a curve in this manifold, and then it has a boundary, and this is some finite set of boundary points. So there's a Legendrian. Another example is cotangent bundles. Conveniently, I've drawn a cotangent bundle, and you can run essentially the same examples. Here, the symplectic form is a little bit more prescriptive. We want, in local coordinates, that the symplectic form to be d momentum coordinates, wedge d position coordinates. And this has a standard expanding vector field, which doesn't look like what I've drawn. Instead, it just expands directly out from the 0 section. And in local coordinates, we can give it by that formula. It vanishes identically on the 0 section. And the skeleton is therefore the 0 section. Now, any to construct Lagrangians in a cotangent bundle, take any smooth submanifold of the base of X, I'm calling it, and take its conormal. So this is the bundle of the restricted cotangent which vanishes on the tangent space of your submanifold. Anyway, that gives you a Lagrangian. In particular, that witnesses that the zero section is Lagrangian. It also tells you that the conormal to a point, which is just the entire fiber at a point, is also a Lagrangian. So here we have another Lagrangian skeleton because the zero section is Lagrangian. Anyway, there's a reason that both cotangent bundles and surfaces have Lagrangian skeleta, but that's not actually what this talk is about. Anyway, if you wanted a singular Lagrangian, you could take a stratification or some singular submanifold and take the union of the conormals of the strata, and that'll give you a singular Lagrangian. And if you want to know what does a Legendrian look like in the boundary of this, well, it's just sorry, we took a disk cotangent bundle. So we picked some arbitrary metric, cut it off, and it's going to have a contact boundary. And any of these Lagrangians that we produced have Legendrians for their boundaries. Okay, so what I'm going to want to do is take some Legendrian, in this case a smooth Legendrian, and I want to thicken it in the contact directions, where the contact directions is the kernel of our contact one form alpha. So the setting, we have a contact manifold Y alpha, and we have a Legendrian submanifold in there. Put that chalk down. So we're going to take some tubular neighborhood, some closed tubular neighborhood of the Legendrian, and we're going to quotient it by this Rabe line field, which is the kernel of D alpha to identify it. We can actually turn this into a vector field, but for our purposes, it's enough to say it's a line field. It's a canonical line field associated to the contact form alpha. So we take this tubular neighborhood, we quotient by this line field, and we get a symplectic manifold, which one can check is isomorphic to a closed neighborhood of the zero section of T star inside the cotangent bundle of the Legendrian we started with. And so one thing we can ask is, can we lift back up? And this is going to be my thickening. And it turns out for smooth Legendrians, there's a Legendrian neighborhood theorem that, among other things, says yes, we can find a lift. So there's a lift that sends L back to L, and which pulls back this one form alpha to the standard one form on a cotangent bundle. And so this is everything we could ask for from a thickening of a Legendrian. Okay, why would I care about that? And this is it's a very reasonable question. It's like bizarre classical construction. And the reason is that there's a general expectation that Floer theory for the Lagrangian is equivalent to Floer theory for the thickening. So maybe I should take a little bit of time and say what I mean by Floer theory for the Lagrangian and Floer theory for the thickening.
L is a Lagrangian?
Oh, sorry, L is a Legendrian. Yes, L is a Legendrian. So Floer theory in this setting, I just mean these rigid holomorphic curve invariants of the dynamics of my contact manifold. So so remember there was this Rabe vector field, and it depends on the contact form that I choose, but Floer theory is a machine for producing invariants that don't depend on the contact form, that any Rabe vector field, whatever that means, will satisfy these invariants. And that tells you things like any one form that you put on Y, this vector field there's going to be a chord from L to itself of this vector field with some which is shorter than some fixed number. This is the sort of statements that you get out of Floer theory. So Floer theory for L is a kind of question that is an interesting thing in dynamics and also in mirror symmetry. And Floer theory for sigma, well, in this case I mean dynamics which are adapted to this thickening in some sense. Now, I could do both of these. They're both nice theories. And the expectation that they're equivalent is useful because sometimes I don't have a singular, or sometimes I don't have a smooth Legendrian, I have a singular Legendrian. And while people know, I don't, but some people, many people do know how to do microlocal sheaf theory for a singular Legendrian, it's not as clear how to do Floer theory for a singular Legendrian. So next week we might see another way of doing Floer theory for singular Legendrians at John Pardon's talks, but I don't yet know how to do Floer theory. So what I would like is a way of thickening these singular Legendrians in the same way as I thickened a smooth Legendrian. So the question is, can we do this for a singular Legendrian? So finding a tubular neighborhood, that still works. Projecting, that still works. And then we can ask, does there exist a lift? And we want a lift that, again, sends L back to itself, and for which the pullback of the contact 1 form makes this quotient x into a Liouville domain. So the key condition here is convexity. We have a symplectic, x is naturally symplectic, but can we, we can generally pretty easily find some primitive 1 form, but finding a convex primitive 1 form is non-trivial. Okay, so I'm going to say right now, I don't know the answer to this question. I don't even know any theorems towards this question, but I think it's a question that's worth thinking about. So how would you try to approach this? Well, if you try to do the straightforward thing, there are 2 steps. First, you can try to construct local lifts near each of the singularities. And then you can try to patch those lifts together. So I'm not going to talk about constructing the local lifts near the singularities, but if you were to restrict to a nice class of singularities, like the so-called arboreal singularities, then maybe that's a tractable problem. Problem 2 is, again, maybe tractable. And I'm going to say what kind of things you would need to do it. It might not be tractable, but we'll see. We'll see. Anyway, because these are symplectic, these lifts are required to be symplectic, they're Rabe graphs of each other. Kind of one is and if I start with one lift sigma, then a different lift sigma prime is obtained by flowing sigma for a small amount of time along the Rabe. And this small amount of time can depend on x, on the point in x. So it's a Rabe graph for some arbitrary smooth function from x to r. And if you look at what this does to 1 forms, well, it just modifies the pullback 1 form by d of that function. So if we're patching 2 of these things together, then we should imagine that they live over an interval. And on one end of the interval, we have kind of f equals 0 because we have kind of the initial sigma. And on the other end of the interval, we have some strange f for the sigma prime. And we want to interpolate an f which equals 0 here and is the prescribed f over here in a way that maintains convexity over the entire interval, or over the entire thickening x on that interval. Anyway, it's quite easy. We could just take df and apply a cutoff function to interpolate without convexity. But if we wanted convexity, it's a lot trickier. So if we cut this into time slices, this breaks into a problem about Liouville domains and Lagrangian skeleta. So the problem I'm going to state is not exactly what you get by breaking into time slices, but if you can solve the one I give, you can probably solve the real problem and vice versa. I think the techniques involved in these 2 problems are very similar. So the question that I want to ask is, if you have some Lagrangian subvariety in a symplectic manifold with boundary, consider the space of Liouville forms with that Lagrangian subvariety as its skeleton and omega as the derivative. So we've specified the skeleton, we've specified the symplectic form, and all we're allowed to do is change the actual 1 form. But we always need to have convexity. Is that space of things connected? Anyway, I don't know any good theorems in this direction, as I said. There's a bunch of technical lemmas in a book of Zülebach and Ellie Ashberg, but they're mostly concerned about something called Weinstein domains, where the main piece of structure that is interesting is a Morse function on top of this Liouville form. And if you try to translate their lemmas into statements here, usually their assumptions are much stronger than we can actually verify. Anyway, that's it.